Welcome, everybody. We're really happy to be with you today. Uh, I guess I should just start off, since we just finished Veterans Day, to once again thank all our servicemen and women for the selflessness they displayed and continue to keep us all safe. Uh, Look, I'm here just to talk a little bit about PTC and how PERC fits in here. And Randy and Art are going to do the heavy lifting here and give you the update on 8.6 and a couple other exciting things going on with the technology. Just that if you're not familiar with PTC, we're not going to give you a history on it. Just to let you know, it's a really vibrant, dynamic, thriving business that's been around for a long time. You can see here that we've had a multiple series of technologies that have evolved over time here that's put PTC in a leadership position for many technologies, and it's playing an important part in disrupting the digital world here. And as PTC continues to have a big influence with multiple innovations here in the past, currently, and will continue in the future, we want to make sure that you have some confidence that PTC is going to be around. We've been around for 35 years. We got a market cap of $14.5 billion and growing consistently. Our annual recurring revenue is $1.5 billion. Our total revenue is $1.8 billion. You can see we have a nice dispersed business around the world, in all regions in most countries of the world. The customer base is diverse, as you can see in the bottom left, with a very strong federal, aerospace and defense, automotive, electronics, high tech, as you might guess, industrial, heavy equipment. And so you can see that it's PTC is just a very well balanced company financially, geographically, technology, verticals. And you can see in the business transformation by the product line in the bottom right, that the products are also that way and give really companies the technologies that, frankly, we all need if you do anything with things. Whether you use them, build them, design them, service them, deploy them, then these are the technologies here that PTC provides that allows you to optimize those technologies in ways you probably never thought possible, frankly. So today we're going to talk about PERC, but when you talk about PTC and the products that we have out there in the marketplace, it's hard to find a thing in the world that does not use PTC technologies. As you can see here, that virtually 100% of Fortune 500 aerospace and defense companies are using PTC technologies. 100% of industrial machinery companies in the Fortune 500 are using PTC technologies. Almost all of the automotive companies, as you can see here at 82%, are also using it. It's almost everywhere. And so, we're talking here about PERC today, one of those technologies. It has an interesting interaction and play with Internet of Things that Randy is going to refer to a little bit later, I think right before he goes into the 8.6 details. And look, I just want to, really leave you from a PTC standpoint with feeling good about doing business with us. The company is really strong financially on the top line, as you can see. I'm not going to list everything. I highlighted in green some of the things that you might be interested. A lot of growth rates on the top line. ARR stands for annual recurring revenue, by the way. And then on the bottom line as well, you can see cash flow. By the way, free cash flow. I know we're not all financial experts here. So free cash flow stands for profit. And so, cash from operations is up 18%. Profit is up 21%. You can see revenue across virtually all products continue to grow, and the market cap continues to grow. So PTC is very strong. We'll be around for a very long time to continue to support you as you're using PERC. And then, I'll leave you with this and turn it over to Randy, that we created inside of PTC what we call the Focus Solutions Group. And this is the division that we're in today. Randy, Art, Melissa, me, we are all part of the Focus Solutions Group. And we created in the company this division that takes really important technologies to focus on them completely. So unlike some other technologies in the company, the resources in FSG, Focus Solutions Group, are 100% dedicated to these products. We don't have a centralized development organization or a technical support organization or other types of functions where PERC only has a part of their attention. It's all of it. So Randy and Art, for example, will do, all of the technical functions in their team for the PERC product. So we're committed. We're building these important products. We're supporting them, and we're always looking for new and innovative ways to use other PTC disruptive technologies to integrate with PERC to make you successful with your products. And so I'm going to turn it over to Randy. If you don't know Randy and Art both have been around for a while in this technology world here. Randy's had lots of experience with all kinds of technologies in the past, hardware, software engineering, scientific workstations, all kinds of things. And both of them bring well over 20 years of embedded system domain experience. You're really talking to the two people who have real-time systems, Java, compiler experience. Really, I'm not going to say necessarily are the fathers of the best concurrent garbage collection technology, but they pretty much are, and a bunch of other stuff, that they'll talk a little bit about later. So welcome, and I'm expecting you're going to hear some really great things today, and we welcome your feedback as the presentation moves on. So Art, if you'd like to take it, that'd be great.
Okay, it looks like I've got it now. My name is Randy Rorden. As Joe introduced me so eloquently, thank you so much for those comments and praise. I don't know if I deserve it all, but I'm here to talk about, first of all, the Developer Tools Group within FSG, the Focus Solutions Group at PTC, introduce you to our team. Our Developer Tools subgroup, if you will, has a mission of providing efficient development environments to our customers so they can build intensive and native and embedded and real-time mission critical applications. Our focus is to be a trusted partner to our customers. And we do that by responding to their needs quickly. We provide product updates, maintenance updates, bug fixes, also training and consulting, and of course, day-to-day support, answering questions and dealing with issues that as they come up. So within Developer Tools, we have some mission critical tools in two areas. One is the Ada language. We have a group that develops the Apex Ada and Object Ada products. These are Ada compilers and runtimes, and of course, associated tools for Ada software development in mission critical systems. They are used heavily in aerospace and defense solutions, and these products have been around even longer than PERC has been, and it's been a long time. So we're really proud to have the Ada products available to our customers as well as PERC, which is a real-time Java virtual machine runtime and tools for developing mission critical systems in Java. And we'll be drilling down into that now. So let's talk about PTC PERC a little bit. But we have a group, as Joe mentioned, also that we have a dedicated team of R&D staff, product management folks, quality assurance, technical support, training, and especially we have dedicated sales account specialists and account representatives. That isolates us a little bit from the day-to-day activities of PTC generally, because we're basically a business unit within ourselves, and that gives us the ability to focus on our customers and on their needs specifically, And I think it's a great advantage that we've been given this responsibility of running the show, if you will, for the PERC products. We have access, of course, to all the PTC resources out there, and you go to their website, and you'll find us prominently featured, and we have access to many of their resources. But we have our own development team and our own support teams. Our team has got, as Joe mentioned, over 20 years of embedded systems domain experience, and we have development experience in Java, real-time garbage collection, embedded Linux, etc. So what's PERC? PERC is a clean room Java virtual machine, we call it. And clean room means that we are not dependent on some source code for our core JVM from some third party, such as Sun Microsystems or Oracle. That Java virtual machine core is built from scratch and purpose-built for embedded systems, and not dependent on any third-party licensed technologies. We develop the JVM to the Java Standard Edition specifications. That's the most popular one out there. It's the one you would normally use on a desktop PC, for example. And there are, of course, the abilities to add on Java Enterprise Edition libraries to the PERC JVM as you need to. So it's not entirely encapsulated as standard edition. You can add on your own stuff as you need it. We include the Java Standard Edition 8 libraries. Those libraries are coming from the OpenJDK open source project. Just the libraries are coming there, not the hotspot VM or any other components that are unique to Oracle or any other JVM, traditional JVMs. That part is ours. We include developer tools that can help you optimize and run your applications on PERC, and we'll talk about a couple of those in a minute. Most importantly, PERC supports sub-millisecond response times down into even hundreds of microseconds. And that's a critical feature of PERC and unique to PERC. PERC is able to protect your Java software from reverse engineering, and we're going to get into that in just a moment. And it is deployed in real-world products and been out there for well over 20 years now. Java has many, many benefits. It's a high-level object-oriented language. It has automatic garbage collection, unlike, say, C++. It can find and recover the memory used by dead objects that are no longer referenced by your applications. And you don't have to worry about managing that object space manually in your code. Therefore, it's safer and more reliable compared to C++ and C. Just saw an article the other day. The U.S. National Security Agency is suggesting that people use memory-safe languages for their applications, like Java, and to avoid having to get into situations where you failed to properly manage your memory and could obviously cause threat actors to make inroads on your application and compromise security. Java has built-in threading and exception handling. It has built-in libraries for everything under the sun: file I/O, network I/O, concurrency, database access, etc. And there is a huge ecosystem of third-party libraries and frameworks and tools out there for helping you develop your Java applications and getting you started without having to build, basically invent the wheel from nothing. Java is taught in literally every major university, any technical university out there. And there are millions of Java developers out there available to hire and use in your application development teams. But one of the big downsides of traditional Java is that it can't do real-time. So real-time systems have deadlines. Whether it's an input coming in from a sensor, you have a deadline to produce some output, some computation and output based on that sensor data. You may have periodic tasks that need to be accomplished on a regular basis. They have deadlines to accomplish those tasks, and that may happen recurrently every 10 milliseconds or every 2 milliseconds or whatever. Or you may have low latency data streams, an opportunity to process data coming in off a network, for example, streaming in, and you need to process that data and form an output within a particular latency requirement. So traditional JVMs have unpredictable timing, and these are caused by many reasons. The most common referenced cause of unpredictable timing is the stop the world garbage collectors that occur. So when a Java thread is executing their individual code, and then an object needs to be allocated, or the garbage collector just finds that there's not enough free memory available, it basically must stop all Java threads from running while it relocates memory and objects in memory so that it can make room for larger object allocations. Just-in-time compilers can interrupt execution basically unpredictably anytime. And the traditional JVMs leave thread scheduling control to the operating system. And so you don't necessarily get the thread that you want to run, even if its priority is higher, to run when it needs to. Page faults on the OS can also cause delays and unpredictable slip of schedules. Priority inversions are another situation where you can get into cases of a mid-priority thread preventing a high priority thread from taking a resource that's being held by a low priority thread. They kind of invert the priorities as a result of that. And timing jitter occurs when you're basically getting some delays in doing wake ups and execution on a periodic basis, and your timing is based on a relative time, and you can't keep up with the time delays that are occurring. Object allocation delays are another reason. If you're allocating an object and there's no room, then the garbage collector may kick in, or you may take longer to find the available object. So real-time systems can't use an Oracle JVM or an OpenJDK JVM. And a lot of Java developers out there don't know that there's a real-time Java product available, and that's PERC. PERC has been designed for real-time. It has a patented real-time garbage collector. It doesn't cause stop-the-world collections. It doesn't shut down Java threads to do garbage relocation and defragmentation. It has ahead-of-time compilation options, and we'll talk about that in the next slide. It also does explicit thread scheduling control. So PERC decides when threads run and selects the highest priority threads to run on the cores that are available in the operating system at the time. And the operating system has no choice but to execute the threads that it provides. We also can do page locking and physical RAM, so we don't get the delays that can occur with page faults. And we have a built-in priority inheritance protocol that operates opaque and transparently to your application. You just set the priorities of your threads, and it takes care of any priority inversion issues that might come up. We have jitter-free timing APIs that use absolute times as opposed to relative times that you can schedule your periodic tasks against and be guaranteed that those will occur on schedule. And we have deterministic memory management that is constant time allocations. So PERC makes Java applications ready for real-time capabilities. This is an example of the GC stress demo, the garbage collector stress demo. The demo basically runs a background thread that allocates memory very quickly. It actually is using a least recently used cache and basically removing objects in the cache and leaving holes in the heap memory that need to be filled with new objects or coalesced into such that the larger objects can be allocated. The red line on the left, this is the OpenJDK 8 64-bit product running this test. The red line shows the heap usage, and you'll see a sawtooth pattern there as it rises and drops. Each drop is indicative of a major garbage collection cycle that occurs as the dead objects are collected and reallocated and memory is coalesced. The blue lines are the high priority timing thread that executes every 100 milliseconds, and the amount of delay beyond the 100 millisecond expected periodic rate is graphed on this display. So you can see that the majority of the blue lines are down at about 100 microseconds or so, but they jump to as high as 100 milliseconds, or even higher, up to 1.4 seconds is the maximum delay in that case. If you look on the right-hand side, we've got PERC 64. Memory usage is steady. The garbage collector is keeping up with allocation rates. Doesn't have to jump up and down like in the sawtooth pattern you see. And more importantly, the high priority timing thread is maintaining timing below 178 microseconds maximum delay. So that 1.4 seconds versus 178 microseconds max delay is literally 8,000 times faster. So the ahead of time compiler I mentioned earlier is the ability to compile Java bytecodes to native instructions, x86 or ARM processor instructions, for example, prior to running in the virtual machine, just like a C compiler does. So we have a couple of tools that use ahead of time compilation. The ROMizer on the left will statically link Java classes and compile the methods in those classes to native code using that AOT compiler, and embeds that in the PERC virtual machine executable. You end up building a custom PERC VM with that AOT code embedded in it, and that runs directly on your target platform. In this case, you see a Raspberry Pi, which is supported by PERC. The AOT code then executes just like native code would, and you don't have to distribute, for example, your jars or class files. They're all embedded inside the virtual machine. Alternatively, you can use the PERC Accelerator or PXL tool. This augments an existing class or jar files with native code, again, generated by the AOT compiler. But those augmented classes then are detected at runtime during dynamic class loading by the PERC virtual machine. So those augmented class files are loaded, and the native code then is dropped directly into heap memory, into RAM, and that is where it executes as is. And so it doesn't have to go through a just-in-time compilation pass or cause any delays as a result of that. So you can still do dynamic loading if you wish, and still get the benefit of AOT code available to you. So an important part of AOT is that it protects you from reverse engineering of your applications, and that means the PERC ahead of time compiler turning that bytecode into native code, just like a C++ compiler. Then the class and jar files can be removed from your deployed systems. You don't have to deploy them; they're all embedded in your JVM. And if you use the PXL tool, by the way, you can null out the bytecode that's in those class files. So only the native code is visible in the class file. Resource files are also needed often to run applications. These are resources like configuration data, XML, schemas, data translations, strings, etc. Those can also be packaged inside the PERC binary through a simple mechanism with a zip archive, and attach that to the JVM, and it gets incorporated and encapsulated in the PVM binary. And it can also contain code and data then basically for the entire application. You can even put file system code in there. You can put files in a zip archive and deploy them inside the virtual machine. So you end up with a single native binary for your application. PERC is great for the Internet of Things and industrial IoT solutions, especially at the layer of the edge gateway, where it's mentioned here, where you can run Linux on ARM or x86 platforms with an edge SDK, such as the ThingWorx SDK, which is available in Java. You can also run concurrently with C and C++ processes as you wish, and use popular manufacturing protocols like OPC UA to communicate with edge devices, sampling data from sensors and activating actuators. And those can be running on bare metal, RTOS, or C++, or even PERC if you wish, as you see fit in your IoT architecture. One example of a PERC success is at Siemens Energy. This is a power plant distributed control system. It's been around for well over 16 years, I think now. It's an embedded PC technology with real-time Linux. The PERC JVM supports automation function cycle times down to about 20 milliseconds to keep up with the data processing of generators, for example, turbines doing electrical generation. The application is almost entirely written in Java. One of the benefits that Siemens Energy saw in the using Java is that they could write both their control system applet code as well as their user interface code in the same language, and so it has an integrated capability for their application requirements. They can deploy it in a standalone or redundant two-system configuration with high availability, and they use point-to-point Ethernet and raw datagrams sockets to transmit data between the equivalent pairs. It's configured by end users via graphical function diagrams. You can drag and drop and set up the controls that you want to view and maintain. And they can do atomic switchover to a different configuration, basically on the fly as it's processing existing data, which is very helpful for their needs in keeping 24/7 operation of their power plants. This system has been deployed in well over 3,500 power plants worldwide. So it's very popular and really helpful to Siemens Energy. So as an overview, PERC has real-time response. As I mentioned, we support Java SE8 libraries. We have 32 and 64-bit versions of PERC on Linux with x86 and ARM multi-core family processors. You can mix ahead of time, just in time, or interpreted execution modes for your application. We have IDE plugins for Eclipse to help you do debugging and native development if you wish. We also have some visual tools called pConsole and pProfiler that let you monitor the state of the VM and also do basically profiling of your application to find out where you're spending most of your CPU time. And we have something called a virtual file system, as I mentioned earlier, the ability to embed a file system within the JVM itself and use that in place, for example, as from your target system file system. Gives you greater encapsulation and control over the starting point of your application. All right, I'm going to hand it over to Art Dyer now and let him talk about our PERC 8.6 release. Go ahead, Art.
Thanks, Randy. The PERC 8.6 was released in July of 2022. This was a change from our previous release cadence, which had us releasing once a year in September. As before, this release includes both 32-bit PERC Ultra SMP and 64-bit PERC 64, and supports both 32 and 64-bit Linux x86 hosts, and 32 and 64-bit Linux on x86 and ARM family processors as targets. This includes the latest OpenJDK fixes and patches as of this date, which, if you're keeping track, is 8U332B09. It includes enhancements to improve your build process, to improve the runtime, and to aid you in development and debugging of your application. And we will drill down into each of those sets of enhancements next. To make your build process a bit smoother, it's now possible for an x86-64XL image to exceed 2 gigabytes. Now, ever since PERC 64 was introduced, it has been possible for an XL build, that is a build that does not use compressed pointers, to have a Java memory heap up to 320 gigabytes. But the image, which is the thing that comes out of the ROMizer that includes all of your statically linked classes and ahead of time compiled bytecode, native code compiled from bytecode, that was limited to 2 gigabytes. And it's now possible for that to exceed 2 gigabytes because we're using a different code model than we were before. On the ARM family targets, XL images can now be up to 4 gigabytes. And they also have a heap capability of up to 320 gigabytes. We have improved the speed of the Ramizer post-processing step. If you're already a PERC customer and you've watched the build, you see that it Ramizes once and this is for a non-XL build, one that uses compressed pointers. It Ramizes once and then links and then Ramizes a second time to patch the relocations that are in that linked code. We've now made that parallel so that if you are running on, for example, an 8-core host, you will see the time for the post-processing step go down by a factor of 7 point something. Both the Ramizer and the PERC accelerator now allow you to use class patterns for exclusion as well as inclusion. For years, you've been able to use a pattern to include all the classes in a package or even a hierarchy of packages. But if there was even a single class in that hierarchy that you didn't want, you couldn't use the patterns because there was no way to eliminate that one class. Now you can use patterns to exclude as well as include packages and classes. The Ramizer and PXL also both have a new command line argument that allows you to wait for a license if all of your licenses are in use by other people doing builds. It will retry for a license after an interval that you specify and ultimately give up after another interval that you can specify, so that your build doesn't simply die if all of your licenses are in use at that moment. And we have enhanced the resource archive and resource trim options to make it easier for you to embed zip and jar files in your applications as resources. The PERC runtime has some additional features. The virtual file system that has been there for, I guess, about a decade, previously supported only the APIs in java.io. Now the classes and APIs in java.nio are also able to use a virtual file system. We have added support for the MX beans in the Java Lang management package. These are APIs for monitoring and managing your virtual machine. The PERC VM APIs that have been there for years are still supported. And in fact, many of the MX Bean APIs are actually built on top of the VM APIs. But this provides you a standard way rather than a proprietary way to monitor your virtual machine. We also include support for one unofficial MX Bean from the ComSun management package. This is an extension of the operating system MX Bean from Java Lang management. One thing we do not support is the MBean server from JavaX management. This is a facility to support remote monitoring of the virtual machine. And for that, we support the pconsole utility, which is included in the PERC distribution. We have also enhanced the PERC shell to support secure remote access. Now, since it was introduced, the PERC shell has included the ability to access it remotely via Telnet using a built-in Telnet server. And that capability is still supported, but Telnet is inherently insecure. For one thing, the Telnet server included with the PERC shell does no user authentication, and there is no encryption of the traffic that flows back and forth. So someone who's able to monitor your network could see what you're doing to the VM and could even connect to it themselves and disrupt it. So the PERC shell server now supports access via Unix domain sockets. You access that when you run the shell with the command line option --Unix, followed by a path name that you specify. That can be any path at all, but the final component of it must not exist. The PERC shell will create it for you as it starts up. You can put that any place you want, and so you can use Linux file permissions on the containing directory to restrict access to just the people that you want to be able to connect to that socket. Locally, you can connect to the socket via the SOCAT utility. SOCAT, or socket cat, is a general purpose utility for connecting two endpoints. If you give it a hyphen as the address of one of the endpoints, it will use your standard input and output for that side of the connection. So by entering the command socat hyphen and then the magic word Unix connect followed by the path that you specified when you started the shell, you can now have your standard input and output connected to the PERC shell. Remotely, you can invoke the same socat command using SSH. SSH will perform the appropriate user authentication and will then encrypt all of the traffic that goes back and forth so that your remote monitoring and management is secure. To ease your development and debugging process, we have added two features: runtime checking of JNI calls and a user-accessible low-overhead event logging mechanism. PERC's runtime JNI checking is similar to OpenJDK's -X check JNI option, but with some PERC-specific features and PERC-specific syntax. When you enable checking, it will detect errors that are commonly made by JNI programmers, such as passing invalid data, perhaps passing a method ID when a field ID is required, or passing a null reference in a situation where null is not allowed. It will detect failure to check for an exception following a JNI call. Most programmers forget to check for exceptions, and unlike Java code, where an exception must be caught or eventually will percolate all the way up and kill the thread, in JNI, you may go many additional JNI function calls before that exception is ever detected. It also detects uses of the various get methods without calling the corresponding release methods. The problem with that is that if you call, for example, get string UTF chars, that requires the virtual machine to pin an object in memory so that it doesn't get moved around by the garbage collector while your native code is still using it. If you forget to release the object, then that object and the region that it is in become ineligible for defragmentation. If you do this a lot, as one PERC customer actually did a few years ago, you get into a situation where there are pinned objects in every region of the heap. Defragmentation becomes impossible, and eventually you are unable to allocate large objects. To enable JNI checking at runtime, you specify --check JNI on the PVM command line, and there are a couple additional options you can also include. You can control the level of reporting that you want by specifying one of errors, warnings, or strict. Warnings is the default. Most of the warnings that get reported are warnings about exception checks that should have been performed and weren't. The difference between warnings and strict is that strict will report missing exception checks even when no exception actually occurred, whereas ordinary warnings are only produced when an exception occurred that you didn't check for. You can also specify a couple other options that are independent of one another. Trace all will cause stack traces to be produced for warnings as well as for errors. The reason that those are not produced by default is simply the volume of output that you get. You can also specify no abort, which says that even after a fatal error, the VM should be allowed to keep running. Now, I will say that after a fatal JNI error, a crash typically follows pretty soon, but if you want to let things keep running after the error occurs in order to see what's going to happen, you can do that. We have also packaged an event logging utility that we have been using for years internally. We have now packaged that for your use. If you've ever received an instrumented build from us in order to track down a bug, you may have received code that was using this event logging system. This allows you to log events both from Java code and from your native code. It's very low overhead. Each thread gets its own ring buffer so that we don't need to do any kind of locking or memory fences in the event logging code. That's important because locking and memory fences, if you're trying to track down a concurrency problem, will alter the thread timing and possibly mask the problem that you're trying to debug. For the native code, we use preprocessor macros so that there is no overhead for a C function call. For logging events from Java, you need to call events of one of our proprietary, or rather call methods of one of our proprietary classes. But the AOT and JIT compilers intrinsify those calls to inline instructions so that you don't have the overhead of a Java method call. You don't need to worry about putting event logging code into your application and leaving it there, because as long as event logging is disabled, each event log is just a Boolean check and a branch around the logging code. So the overhead is very low. Events are dumped automatically upon a crash. You can also choose to dump them on demand or upon exit from the VM. Events are dumped in a binary form, and we provide a default event coder that will render them into a human readable text. But we also allow you to customize that event decoder so that you can print them in a form that is more meaningful and easier for you to read. All you need to do is implement an interface to do that. This is what the logging API looks like. In Java, you would import the VM class from COM Mnemonics PVM, and then you have three choices of ways to log events. Each of the log event methods takes a short, which is an event code that you choose. The most common way to log an event is by passing two 64-bit data values, but you can also pass an object, in which case we will log the address of that object in the heap. And you can pass a string, and we will log the first 16 characters of that string. You can call the dump events method at any time in order to dump the events that have been accumulated up to that point. You might do this if you detect some error condition and you want to know how you got there. Another thing you may want to do is with the perk thread class of the COM Mnemonics PVM package, you may want to call save dead threads and give it an integer. The reason for doing this is that when a thread exits, its event log buffer goes away along with it. If you're dealing with some sort of problem that occurs right around the time a thread exits, you may want to keep that thread around in order to be able to log the last events that it did before it died. Save dead threads will keep the n most recently used or n most recently exited threads so that you can see their events after they've died. When you compile your Java code, you will want to make sure that perklib.jar is in your class path for the Java compiler if you use Java-C. If you use the JDTC utility that we supply, that's done for you automatically. In your native code, you will include pvm.h, which is a header that we supply. Then you only have one way to log events because you can't overload C preprocessor macros the way that you can overload Java methods. PVM log event again takes a short code that you choose and two 64-bit data items. There is a similar event for dumping events on demand. PVM dump events will do that. When you compile your native code that logs events, you need to make sure that the include directory underneath perk home is in your search path for header files. To use event logging, you build PVM as usual. There are no additional build time options that are necessary. The event logging system is always there in the runtime, ready to use it. To enable logging at runtime, however, on the PVM command line, you need to specify -- event log. And then there are a few additional options you can also include. You can tell it the size of the event buffer you want to use, and that is a number of events. If you want to know how much space that it's taking up, the -sdump option on the PVM command line will tell you that. Other options may include on exit, which causes events to be dumped upon exit from the VM. And you can specify the file name for the event log with a template that may include a couple escape sequences. %P is replaced by the process ID of the PVM. %T is replaced with a timestamp that goes down to the level of seconds, so that you can dump multiple event logs, and as long as they are no less than a second apart, the second one will not overwrite the first one. If you don't specify a file name or a template, the default file template is PVM events followed by the timestamp. No matter how you specify the file name, a .zip extension is always added to it because the event log dump is a zip file with one entry for each of the threads that is included. If you are using event logging from Java code, you will want to make sure that you use a JIT threshold of 0 unless all of the Java code that logs events is AOT compiled. That way you don't have to wait until the method gets JIT compiled before the logging method calls are reduced to inlined instructions, so you don't have the method call overhead. To decode an event log, we supply a Java class called decode event logs in the common mnemonics util package. That is in perktool.jar, and you run that on any JVM, giving it the name of the event log dump file as its argument. It produces output similar to what you see here. One line per event. Each line includes the timestamp since the epoch. It includes the thread ID, which is the Linux lightweight process ID, the thread name, the event code that you chose, a line number for events logged from native code, and then your two data items rendered as both decimal and hex and as a string. Events are displayed in reverse chronological order, so the last thing logged is the first thing that you will see at the top of the output. Thread names are truncated to 16 characters because of a limitation of the pthread library. And the line number is always 0 for Java events because we aren't able to do something in Java similar to the under line under thing of the C preprocessor. But you can write a custom event decoder that will produce output easier for you to read than the default. To do this, you need to implement the decoder interface that is declared inside the decode event logs class. There's only one method of that interface that you must actually implement. The decode method takes an instance of log entry and a thread name for each event. Decode event logs itself will handle the reading of the log file for you and call your decode method once for each event. Inside that decode method, you print whatever representation of the log entry you want. Log entry is an immutable class that contains the fields that you see here on the slide, which correspond to the columns that were displayed in the previous slide. To use your custom decoder, you pass its class name as the second command line argument to decode event logs following the event file name. There are some additional methods of the decoder interface that you could choose to implement. Those are documented in the PERK user manual. Now, the target system requirements for PERK 8.6 are the same as they were for 8.5. This is essentially a Red Hat Enterprise Linux 7 or 8 or any other distribution derived from that for x86. For the ARM family processors, you need a Raspbian Stretch or better, Ubuntu Mate 16.04.2 or better, or Debian 9.1 or better, with the various components that you see there on the slide. So if we look at this feature set of PERC 8.6 compared to last year's roadmap, we've done pretty well. We have implemented all but one of the features in the roadmap, and we released in July rather than September. In order to make that July date, we omitted one thing from the roadmap, which was the example Ant scripts for building PVM. We will still include sample make files. We will include the Ant scripts in the next major PERC release. And speaking of the next major PERC release, the fiscal 23 roadmap, and we are already 6 weeks into fiscal 23, we will, of course, continue to do maintenance releases as needed for critical bugs that are found either by ourselves or by our customers. But the next planned release will come on our new release cadence in July 2023. That will include all of the open JDK patches and non-critical bug fixes as of that date. Will it include any additional new features? That is up to you. If our customers make us aware of things that they need in order to use PERC better, or if in our interactions with customers we realize that there are things that our customers could use, then we will include those. The next planned release might be PERC 8.6.1 or 8.7, depending on whether it is including new features or is just a bug fix release. Looking further ahead in fiscal 23 and beyond, we are already working on PERC 17. That will be a 64-bit only release, and it will include the Java 17 classes and APIs. Now, you may wonder why we would go all the way to 17. Why leapfrog over 8 other releases instead of simply going to version 9 or maybe 11? The reason for that is that although there are major Java releases every 6 months, only one of those in 3 years is designated for long-term support. Now, Java 8 is an exception. Red Hat has committed to supporting Java 8, OpenJDK 8, that is, through November of 2026. But support for versions 9 and 10 and 12 through 16 has already ended as of now. Version 11 is a long-term support release that will be supported until 2 years from now in October of 2024. Version 17 will be supported for 3 years after that, till October 2027, and that is why we are taking the leap all the way to Java 17. It can be scary to think about taking your Java 8 code and trying to run it on Java 17. But Java is actually very good about backward compatibility, with a few exceptions. Some features that you have probably never even thought about using in your application have been deprecated for some time and are removed in Java 17. This includes RMI activation, Java Web Start, and Java Applets. Some other features like Java FX have been spun off as separate projects that you would need to go and download separately if you want to use them. And then there's the elephant in the room, the one really big change, which is the Java Platform Module System. Now, this was introduced in Java 9. So even if we only went as far as Java 9, we'd still have to deal with it. Java has always had packages in order to group classes. Classes and members can be made private to the package, but anything you want to share with another package must be public, and that makes it effectively global. The JPMS introduces modules as a way to group packages. A module can declare not only which of its packages are visible, but also which other modules are allowed to see and use them. So even public classes and members can be hidden from packages outside the module. Packages cannot be split across modules, so you can't do the trick of declaring a class to be in java.io in order to access java.io's package private features. And these restrictions even apply to reflection. Why would they do this? Here's an example. The School of Hard Knocks creates a set of APIs for data collection and data analysis and publishes those. but those depend on some undocumented APIs that they also wrote. They don't intend for those to be used externally, but they have to be public in order to be used by those other packages. Big Data Corp comes along and creates a product based on those public APIs, which is fine. That's what they were meant for. But they also use some internal APIs that they were never meant to have access to. By putting a module around their packages, hardknocks.edu can control which of their packages are accessible outside and which are not. Java and OpenJDK, as of Java 9, have a new system loader to implement the JPMS. It has a module path, in addition to the class path we're all familiar with. Classes can be packaged as modules or as modular jars, which is just an ordinary jar file with one extra member that specifies the dependencies and access rights for the module. We can say goodbye to sun.misc.unsafe as just one example of things that are no longer accessible. That and other things break lots of people's code. So the developers included lots of backdoors to get around the rules for compatibility. Those were introduced in Java 9, and we were told they were deprecated and were going to be removed eventually, but as of 17, they're still there. There are command line options that will let you add access rights to modules that the developers never intended. Modular jars placed on the class path behave like ordinary jars, and I know that we are now getting short on time, so very quickly, what PERC is going to do with the JPMS, initially in Java 17, we will not be enforcing the module access rules. The system loader will be the familiar Earl class loader as it is in PERC 8. System classes will be packaged in jar files as before, rather than in modules. The class path and boot class path will function as before. Modular jars will be allowed, but will be treated like ordinary jars. The module APIs, we are uncertain how we will deal with those. We need to gain more experience before we commit to how those are going to work. Will we treat every class as though they're in one big happy module, or will we somehow indicate what modules they're in without enforcing the access rights? And there will be no support for JLink, which is a tool similar to the Romizer for producing a custom JRE tailored to your application. In the future, will we fully support the JPMS? That is up to our customers. If we hear customers telling us that they want us to go there, then we will. Platform requirements will be essentially Red Hat 8.6 or other distributions derived from that, or for the ARM family, an Ubuntu 18.04.5 or better. There are a number of resources on the website to help you with PERC development, including white papers and data sheets, as well as resources for customers. Besides the installation kit downloads, some brief tutorials that introduce various facilities within PERC, and a number of technical notes that do deeper dives into specific features. I think that we have left little time for questions and answers. You certainly can email your questions to our support email, and we will answer those questions for you. Randy, is there anything you wanted to add at this point?
No, but thank you. And I'll turn the time over to Melissa to wrap it up.
Great. Well, thanks, everybody. Sorry we didn't get a chance to answer your questions, but if you can please email us at developer-tools-support@ptc.com. I did put that in the chat, or you can just email me directly. You should be able to have my email address since you did register for this webinar, and I will get those questions to the appropriate person to get those answered. Like I said, this was recorded and will be posted on the YouTube channel. And thanks everyone for joining. And we look forward to attending our next session. Thank you very much. Have a good day, everyone. Bye-bye.